All right, what up, everybody? This is Mr. Stan coming at you with another physics video, and today we're talking about electromagnetic waves. All right, so first of all, what are electromagnetic waves? They are waves that do not require a medium to travel, right? So they can travel across empty space, which is unlike sound waves. Sound waves have to have something in between the thing making the sound and the thing receiving the sound that it can vibrate, and that's how the energy travels back and forth. But with electromagnetic waves, they don't have to have something in between. That's why light from the sun can go through the empty space between the sun and Earth and still reach us. Okay, electromagnetic waves move at the speed of light, as it's called, and it's actually the speed of electromagnetic waves. Light is just one type of electromagnetic wave, but all electromagnetic waves move at a speed of 3 times 10 to the 8th meters per second, which is 300 million meters every second. Right, and that's the speed in a vacuum. Right, when electromagnetic waves move through places where there's actually material, whether it's air, water, or glass or something like that, they slow down a little bit. Okay, you might hear the term light year before. Light year is the distance traveled by an electromagnetic wave in 1 year, and it's about 5.87 trillion miles. Okay, so if you could see an electromagnetic wave, if you could slow them down enough to look at them, um, you still wouldn't be able to see them, but this is what they are doing. This is kind of a drawing of what's going on. We learned about electric fields and magnetic fields earlier in the course. Basically, an electromagnetic wave is an electric field which is always changing. And whenever an electric field changes, there's always a magnetic field changing. And whenever there's a magnetic field changing, there's always an electric field changing. So these electromagnetic waves are, because the fields are changing, they're making the other change, which makes the other change again. So they're always moving, right? And you could imagine that what they look like is the electric field is in one direction, maybe up and down. The magnetic field would be side to side, right? So it kind of looks like that. You imagine this is as close to a 3D image as we can put on a 2D slide. Right, so the wave is like moving in this direction, where the electric field is going up and down in the z direction, and the magnetic field is going back and forth in the y direction. And they're transverse waves made up of electric and magnetic components. Okay, just like other waves, we can measure the frequency by how many waves go by in 1 second. And we can measure the wavelength by measuring, say, crest to crest or trough to trough, or any one point on one wave to the next point, to the identical point on the next wave. All right. So scientists have classified electromagnetic waves depending on how long the wavelength is, right, and or what the frequency is. And so radio waves are the largest of the electromagnetic waves, and they can have wavelengths that are about the size of a building, even taller, all the way down to wavelengths that are about the size of a meter. Right, and then after that, you have microwaves, then infrared, then the visible spectrum, which is a small part of the electromagnetic spectrum that we can actually see. So if the frequency of the wave falls in this range, then you'll be able to actually um, see the waves, as they bounce, see the waves as a color. All right, then after visible light, you have ultraviolet, and these are getting really small, like down to the size of the wavelength. They're down to the size of a molecule by now. X-rays, which are about the size of an atom, and then gamma rays, which are about the size of the nucleus of an atom. Now, as wavelength increases, frequency decreases, right? And as wavelength gets smaller, frequency gets larger. Remember, frequency is how many times the wave oscillates in 1 second. Right? High frequency waves have more energy, right? Low frequency waves have less energy. Okay, just like if you had a rope and you were vibrating the rope up and down, the more energy you put into it, the higher the frequency would be. You'd have more wavelengths in a shorter space, so you'd have a shorter wavelength length as well. And so, not surprisingly, the radio waves, which are really long waves, have the lowest energy, and the gamma waves, which are the shortest waves, have the highest energy. Right, and we're going to be using scientific notation when talking about electromagnetic waves, and the reason we do that is to avoid all the long numbers, right? That can appear. So, take violet light for an example, right? Um, the frequency of a violet light, if we round it, is this right here. This is a really long number. And the wavelength is just a really small number with a lot of zeros after the decimal. So when you're writing this out by hand or typing it into a calculator, it's very easy to miscount the zeros, and also it takes a lot of time to get the zeros right. So instead, we work with scientific notation. So this big number here for the frequency, this comes 7.9, and then we count how many spaces the decimal would move if it went from the back of the number all the way to 7.9, and it would move 14 to the left, and so we say it's 10 to the 14th. Here, the decimal would move 7 to the right, uh, and so we say it's 10 to the minus 7th. So using these scientific notation, you're going to see these a lot. Just remember, if you have a positive exponent, that means it's a number bigger than 1, and the bigger that exponent is, the bigger the number is, right? So every time you add one exponent, the number gets 10 times as big as it was before. But with the negative numbers, the bigger this exponent is with a negative sign, the smaller the number is. It's getting closer and closer to 0. Right? So that's an introduction to electromagnetic